After having derived the expression describing the potential energy of electrodes, we determine electric forces on charged conductors. We calculate the infinitesimal force exerted on an infinitesimal area element ds of the surface S of a charged conductor, where we suppose that the conductor has a positive net charge. The surface area element ds of the charged conductor is located in an electric field E double prime due to the charge distributed over other parts of the surface S of the conductor. As a result, the direction of the field close to the area element is the same in its both sides pointing outward from the conductor. By definition, the force acting on a given amount of charge located in an electrostatic field is the product of the charge and the electric field strength. Then the force dF exerted on the surface area element ds containing the charge given by the surface charge density sigma times ds can be written as sigma times ds, times the magnitude of the electric field E double prime. We have already shown that the electric field E due to the total charge distributed over the surface S of a conductor vanishes within the conductor and it is perpendicular to the surface close to the conductor. Its magnitude at the surface is given by the surface charge density sigma over epsilon naught. The charge distributed over the surface element ds also produces an electric field E prime, pointing away from the charged surface. As the figure shows, the electric field E double prime is the same at two corresponding points in the opposite sides of the surface area element ds, whereas the electric field E prime points in opposite directions and only its magnitude is the same in the opposite sides of the area element. Then the superposition of the fields E prime and E double prime outside the conductor is the following. The net electric field E is equal to the sum of the magnitudes of the fields E prime and E double prime, which must give sigma over epsilon naught. Within the conductor they have opposite directions and their superposition gives the difference between their magnitudes, where the net electric field E vanishes. We immediately conclude from the second equation that the magnitudes of the field E prime and the field E double prime are equal. Then the first equation tells us that their magnitudes are given by sigma over 2 times epsilon naught. As a result, the electrostatic force dF acting on the infinitesimal surface area element ds given by E double prime times sigma time ds, is equal to sigma squared over 2 times epsilon naught, times ds. If we substitute the relationship between the surface charge density and the field strength into the right-hand side, then we obtain 1 over 2 times E times sigma times ds, or 1 over 2 times epsilon naught times the square of the electric field strength E, times ds. The result shows that the force acting on a unit surface area of a charged conductor, that is the surface density of the force given by the derivative of the force F with respect to the surface area S, is equal to the square of the surface charge density sigma divided by 2 times the vacuum permittivity epsilon naught, or 1 over 2 times the magnitude of the electric field E due to the surface charge, times the surface charge density sigma. This expression can also be written as 1 over 2 times the vacuum permittivity epsilon naught times the square of the magnitude of the electric field E, where we can recognize the expression obtained for the energy density U of an electrostatic field. Then we find that the surface density of the force exerted on a given surface area element is equal to the volume density of the electrostatic energy at the surface area element. We can also deduce the same result for the force on a charged conductor by applying the principle of virtual work. We determine the virtual work done while an infinitesimal volume element of the conductor at its surface is displaced in the direction normal to the surface. The cylindrical volume element has the base of the surface area S and its height is given by the virtual displacement delta x along the surface normal. The virtual work delta W done on the charged volume element when it is displaced by the force F on the surface of the conductor is equal to the magnitude of the force F times the displacement delta x, since the electric field representing the force is parallel with the displacement at the surface of the conductor. As the result of the virtual displacement, the electric field is reduced to zero in the space occupied by the displaced volume element of the conductor with vanishing electric field inside, but there is no other change in the field outside the volume element, at least to the first order. Then we can assume that the change in the energy of the electric field in the space occupied by the displaced volume element is completely converted into the virtual work done on the volume element. The infinitesimal change du in the energy can be written as the energy density lowercase u of the electric field times the infinitesimal volume element dV. We have already shown that the energy density of the electric field E is given by 1 over 2 times epsilon naught times E squared, and the volume element dV is simply equal to the surface area S times the displacement delta x. By inserting these expressions into the right-hand side, we obtain 1 over 2 times epsilon naught times E squared times S times delta x. From the law of the conservation of energy telling us that du is completely converted into delta W, we obtain that the force F times the virtual displacement delta x is equal to 1 over 2 times epsilon naught times E squared, times S times delta x. If we divide this equation by S times delta x, we can write the force acting on a unit area of the surface of the charged conductor as 1 over 2 times epsilon naught times E squared. Since the electric field E at the surface conductor is equal to the surface charge density sigma over epsilon naught, the right-hand side can also be written as sigma squared over 2 times epsilon naught. Thus we have obtained the same expressions as the ones derived from the superposition of electric fields due to the charges on the different parts of the surface of the conductor. Since force per unit area is pressure, we can define the electrostatic pressure exerted on a conductor is that the charge exerts on the surface of the conductor, that is the electrostatic pressure is given by 1 over 2 times epsilon naught times E squared or sigma squared over 2 times epsilon naught. We note that the formula obtained for the infinitesimal force stating that dF is equal to 1 over 2 times sigma times E times ds can be integrated over the whole surface of the charged conductor. Then the net force F on a charged conductor is given by 1 over 2 times the surface integral of the surface charge density sigma times the electric field strength E over the surface S of the conductor, or 1 over 2 times epsilon naught, times the surface integral sigma squared over the surface S. As a result, the total electrostatic force acting on a charged conductor is completely determined by the charge distribution over the surface of the conductor or the electric field emanating from or terminating at its surface, and the geometry of the conductor. If more charged conductors are present in a system, then the electric field lines connecting their surfaces produce an attractive electrostatic force between the electrodes. Now we determine the attractive force between the plates of a charged parallel plate capacitor. Instead of calculating the electrostatic forces acting between point charges, we will apply the energy theorem. Let x denote the distance between the plates of the capacitor storing the charges plus q and minus q respectively. In order to increase the distance between the plates by an infinitesimal amount dx, the work dw is required to do against the attractive force F, which is given by F times dx. This infinitesimal work is converted into an infinitesimal change in the energy U of the capacitor, that is du is equal to dw. Then it is also equal to F times dx, and the force F can be written as the derivative of the energy U with respect to the distance x. The energy U of the capacitor is given by the charge Q squared over 2 times the capacitance C of the capacitor, where the capacitance for parallel plate capacitors is equal to epsilon naught times the area A of the plates over the distance x between the plates. Then the energy U is expressed as a function of the instantaneous distance x between the plates. By inserting this expression into the force equation and computing the derivative with respect to x, we can write the force F between the plates of the capacitor as 1 over 2 times Q squared over epsilon naught times A, or 1 over 2 times Q squared over C times x. Since the distance x is equal to d at a given position of the plate, and the charge Q on the plates is equal to the capacitance C times the voltage V between the plates, the force F is given by 1 over 2 times the capacitance C over the distance d, times the square of the voltage V, or 1 over 2 times epsilon naught times the area A over d squared, times the square of the voltage V. This formula shows that the attractive force F between the plates can be determined by measuring the voltage V through the capacitor if the area A of its plates and the distance d between them are known. This relationship is used in the working principle of Thomson's absolute electrometer seen in the figure, which measures voltage and the amount of charge based on the balance between electrostatic and gravitational forces. The electrometer consists of a parallel plate capacitor with a fixed plate and a movable one. The fixed plate is a grounded metal disc and the movable one consists of a smaller disc suspended from the beam of a sensitive balance and a fixed guard ring around the disc. Since the gap between the disc and the ring is extremely small, the electric field has some scattering only at the outer edge of the ring and is uniform between the two plates. As a result, the force formula obtained for parallel plate capacitors can also be applied for the capacitor of the electrometer. If the voltage V is applied to the plates, then the movable plate and the ring attain charge, an opposite charge will be induced on the fixed plate, producing an attractive force F between the plates of the capacitor. The force moving the suspended metal disc can be balanced by placing the weights G in the pan of the balance to restore the position of the moving plate in the plane of the ring. If the magnitudes of the force F and the weight G are equal, then we can replace F by G in the force formula, and express the voltage V as the distance d between the plates times the square root of 2 times the weight G divided by epsilon naught times the area A of the plates. Since the geometry of the parallel plate capacitor of the electrometer precisely specifies the capacitance of the capacitor, the instrument allows one to determine the charge attained by the plates at high accuracy from the measured voltage between the plates. Thomson's absolute electrometer is a specimen of a broader class of devices, where electrostatic forces due to the interaction between bodies with excess charges can be measured by balancing them with non-electrostatic forces. As a result, the amount of electric charge or voltage producing the electrostatic field can also be determined. A measuring device based on this principle is called electrometer, which is the version of electroscopes allowing one to perform quantitative measurements of electric charge. One of the simplest type of electrometers is known as Braun electroscope, normally used for classroom demonstration of electrostatic phenomena. We already presented this instrument as a pointer electroscope without a scale when we discussed how to determine the presence of electric charge on bodies. Now we give a more detailed analysis on the version with a scale, functioning as an electrometer. The housing of the instrument is a grounded metal case, which is cylindrical in shape and has glass windows on both the front and the back sides. A vertical metal rod penetrates the top of the case through some insulation and a curved metal scale is attached to its bottom. The electrical contact at the top of the rod is either a metal sphere or a metal plate. A light needle is connected to the vertical support rod by a pin through its center so that the arm is free to rotate around a horizontal axis. The needle is balanced in a vertical position. If the electroscope is charged through the metal sphere, its vertical rod and needle will attain like charges, producing a repulsive electrostatic force between them. As a result, the needle is repelled by the vertical rod, and rotates to a new equilibrium position at a distance proportional to the amount of charge distributed over the needle and the rod. In its new equilibrium position, the magnitude of the repulsive force is equal to the one of the gravitational force exerted on the arm in the opposite direction. The greater the charge, the greater the deflection of the needle, and we can measure the charge attained by the electroscope or an equivalent voltage by reading this deflection on the calibrated scale. If we want to measure the voltage V of a voltage source between its terminals A and B, then we connect these terminals to the metal sphere of the Braun electroscope and its grounded metal case respectively, as seen in the figure. Here the series of horizontal bars between the nodes A and B in the circuit represent the series of cells of a battery used as the voltage source. The case of the electrometer and its parts insulated from the housing form the plate B and A of a capacitor of capacitance C. Then the plates A represented by the insulated parts of the electrometer will attain the charge Q given by the capacitance C times the voltage V between the sphere and the case, and the plate B represented by the metal case will attain the charge minus Q. A given amount of the charge Q is distributed over the needle of the device. If we denote this amount of charge by Q', then we can write it as some constant K times the charge Q, or K times C times Q, where K is less than unity. On the one hand, the force exerted on the needle is proportional to the charge Q'. On the other hand, this force is also proportional to the electric field strength E between the insulated parts of the instrument and the metal case that is produced by the charges Q and minus Q on them. Since both the charge of the needle and the electric field strength increase with the increasing voltage V, the force exerted on the needle increases as well. As a result, the increasing voltage also increases the deflection of the needle. The scale of the Braun electroscope can also be calibrated by applying known voltages to the instrument, so that the electrometer could directly measure voltage. The range of operation of such devices is between 100 volts to 10,000 volts. If we want to measure the voltage V between the two plates of a charged capacitor of capacitance C, then we connect its plates A and B to those of the capacitor formed by the metal sphere and the parts insulated from the case, and the metal case of the electrometer. As a result, the voltage through the capacitor decreases and the electrometer measures a voltage V' less than the voltage V. The initial charge Q of the capacitor is given by the product of its capacitance C and the voltage V through the capacitor. During the measurement, the amount of charge Q distributed over the system does not change, but the capacitor and the electrometer of capacitance C sub L form a series of in parallel. As a result, the capacitance of the system is the sum of the capacitances C and C sub L, and the total charge of the system is equal to the sum of C and C sub L, times the reduced voltage V' between the metal sphere or the plate A and the earth or the plate B. From these two expressions we find that the voltage V through the capacitor can be written as 1 plus the ratio of the capacitance C sub L of the electrometer to the capacitance C of the capacitor, times the voltage V' measured by the electrometer. If the capacitance of the electrometer is much smaller than the capacitance of the capacitor, then the measured voltage is approximately equal to the voltage between the plates of the capacitor. A more sensitive type of electrometer is the unifilar electrometer or string electrometer, utilizing a single fiber or string as the sensitive element of the measurement device. The electric field strength acting on the moving part of the device can be increased independently of the magnitude of the voltage being measured by applying external voltage sources for the electrodes producing the field, as seen in the figure. In the box encasing the apparatus, a fine platinum fiber or a quartz fiber coated with conducting material passes through the electric field E between a pair of metal plates A and B connected to batteries serving as external voltage sources for the field. The voltage V to be measured is applied at the two ends of the fiber, which attains the electric charge Q. As a result, the fiber mounted midway between the two electrodes is deflected by the force of the electric field towards one of the metal plates. The force exerted on the fiber is proportional to the product of the charge Q of the fiber and the magnitude of the electric field strength E. Since the charge Q of the fiber is proportional to the voltage V applied to the fiber, its displacement observed against a scale with a microscope is approximately proportional to the voltage being measured. By applying a proper calibration for the scale, the magnitude of the voltage V can immediately be determined by noting the deflection of the fiber against the scale. The sensitivity of the string electrometer may be increased by adjusting the tension on the fiber and increasing the strength of the field, that is the external potential applied to the electrodes. The later is normally between 50 and 100 volts with respect to ground. We note that there is a bifilar version of the string electrometers where the potential being measured is applied to two fibers passing through the electric field between a pair of electrodes, and the deflection of the fibers due to their mutual repulsion is observed through the eyepiece. The most sensitive and accurate of all the mechanical electrometers are the quadrant electrometers. In these instruments, a paddle-shaped aluminum needle with two wings or a vane is independently charged and suspended inside a drum by means of a metal-coated quartz fiber or a torsion fiber made of phosphor bronze. The drum is cut into four hollow metallic quadrants supported separately on amber insulting stands, and the insulated quadrants are connected diagonally in pairs by fine copper wires. The potential difference V is to be measured as applied to each pair of quadrants, whereas the vane is usually kept at a constant high potential by connecting it to a battery. When the same potential is applied to the two pairs of quadrants denoted by A and B, the vane rests symmetrically between them. If they have different potentials, then a static electric field E is set up between the quadrants, and a force is exerted on the charged vane. For the potential of the quadrants A greater than the potential of the quadrants B, the vane deflects from the pair A of the quadrants to the pair B of the quadrants. The potential difference V is determined by means of the deflection of the vane toward one pair of quadrants through an angle, which is approximately proportional to the difference of potential between the two pairs of quadrants. The angle of deflection is measured by a beam of light projected on a mirror which is attached to the torsion fiber and reflects the light onto a calibrated scale.